we're going to work almost entirely on example problems to make sure you know how to solve these different kinds of problems. First, just a note or two regarding the homework that was just returned to you today. Frankly, almost everybody did very well. Practically everybody got pluses, full credit. It seems like some of you are a little unsure of how to deal with gases or even liquids or solids, which of course was a lot of these problems, or was used on a lot of these processes, a lot of these problems. Remember that an internal energy change for an ideal gas is CV times the temperature change. An enthalpy change is CP times the temperature change, and some students were mixing those. With regards to solids or liquids, like that one problem with the brass plates, it doesn't matter, right? Specific heat at constant pressure is the same as at constant volume. We just call it the heat capacity. As such, the internal energy change equals the enthalpy change equals the heat capacity times the temperature change. Just make sure you have everything done, consistently. Also recall that the first law for closed systems involving a constant pressure process allows you to combine the internal energy change with the boundary work, which is pressure times volume change, and that becomes an enthalpy change. So you could simply write that heat transfer equals change in enthalpy plus miscellaneous work. Pardon me, for those constant pressure types of problems. Some students were using enthalpy change simply in place of internal energy change, and that simply is not correct. So again, make sure you're using the equations properly and consistently. Some students had issues with signs and the usual math errors, unit conversion errors and all that, but I really hardly saw any problems in this homework set. So with that, let's just move on. Last time we ended by looking at problem 530 out of the 8th edition of your textbook. And I kind of talked about it, but we didn't really go through it in much detail. Remember, first of all, that we're dealing with steady flow processes at this point, and most of them are single stream steady flow processes. The first law that one would utilize actually doesn't look a whole lot different than the first law for a closed system, right? Granted, there's no internal energy change term, there's an enthalpy change term now. But besides that, you've got the same general terms. You have heat transfer equals essentially change in enthalpy plus change in kinetic energy and potential energy plus the work. So make sure you're using the right version of the first law when you're dealing with these processes that involve flow. This is the first law for the open system, that is for the control volume, and as such is just a little bit different than that for the closed system. But the problems are not really that more complicated, they're just different. So here we're looking at a nozzle. I read through this last time. Maybe we could, thank you. So as we saw last time, we have a nozzle. So I'm just going to say nozzle. And it says we have steam, so I'll just put an H2O here. It says it enters the nozzle at a particular temperature and pressure and velocity. So let's just let 1 be the inlet and 2 be the exit. And I always like to put the inlet conditions over here by the inlet. So the inlet pressure is 800 kilopascals. Inlet temperature is 400 degrees Celsius. And the inlet velocity is 10 meters per second. So these are all ones. 1 would be the inlet. And then it gives me the exit condition. It says that temperature and pressure at the exit is 300 Celsius and the pressure 200 kilopascals. And then it tells us that we're losing heat at the rate of 25 kilowatts. So that's a rate of heat transfer. So I'll put Q dot. I'm not going to put the subscript CV for control volume. I'm just going to put the subscript that represents the inlet and the exit condition. So I'm just going to put a Q dot 1, 2. And in magnitude, this is 25 kilowatts, which is the same as a kilojoule per second, which is how I prefer to use the units for heat transfer rates. But this is a negative sign, right? To be consistent with our sign convention, we're losing heat from the system, so we have to show this as minus 25. It also gives me the inlet area. So A1 is 800 square centimeters. There's 10 to the 4th square centimeters per square meter, so that's the same as 0.08 square meters. So we'll definitely have to convert into square meters eventually. We may as well do it now. And it says determine the velocity and the volumetric flow rate at the exit. So we're trying to find V2 and V dot 2. Please note that you cannot assume that the velocity at the entrance and exit are the same, nor can you assume that the volumetric flow rates are going to be the same. We have a pretty significant change in both pressure and temperature, so our specific volume is definitely going to change. If the specific volume changes, then the mass is going to occupy either a larger or a smaller amount of space, and we're definitely not going to have the same volumetric flow rate. The mass flow rate is going to be the same because these are all steady flow processes, so that's always constant. But you certainly can't assume that the volume flow rate is the same just because the mass flow rate is the same. Nonetheless, this is a single stream steady flow process, so it doesn't hurt to write SSSF for single stream steady flow. We also know that we're talking about steam, and in fact, if we look at the data that's given, we'll find that all this is superheated steam. So all of our data is going to come out of table A6. Now, I'm not going to bother to put the data here on the board as well. I mean, we know now how to use these property tables. So what equation do we have to solve for? Well, the first law. And the first law for single stream steady flow process is rate of heat transfer minus the rate of work, or power if you will, is going to equal the mass flow rate, and then times the enthalpy change plus the kinetic energy change plus potential energy change. Again, it's a single stream process. M dot in equals M dot out, and we'll just call that mass flow rate M dot. If you want to, somewhere up here, you can put M dot 1 equals M dot 2. It's just equal to M dot, just to remind you, again, that it's a steady flow process. All right, so what else do we know? Maybe we can eliminate certain terms. Well, sure we can. We know that there's no net height change associated with the nozzle, especially in this horizontal position. Even if there was, you need to have a nozzle that's like the size of this building before that height difference would really be something that's not negligible. So we could certainly assume that the potential energy change is 0. And like all nozzles, it's a passive device, right? There's no work associated with any portion of this process. So the W dot term is also equal to 0. So that then leaves us with a somewhat simpler version of the first law. Heat transfer equals mass flow rate, and then times enthalpy change plus kinetic energy change. So, if you think about it, there's not a whole lot to do in this problem. We have both pressure and temperature, two independent intensive properties at the inlet and exit, so we can very easily find H1 and H2. We're given the velocity at the inlet, so we know V1. What about our continuity equation? We know we're always going to have to use continuity or some version of it, so we can find the mass flow rate, because that's just the velocity times area over specific volume. We can't solve this at state point 2 at the exit, right? Because we don't have the exit velocity, but we do have all these data at the inlet velocity. That's right, at the inlet condition. So we're going to use this to find the mass flow rate. About the only thing that we really don't have is more information about the velocity. Well, that's our only unknown, right? We know the heat transfer rate. I guess I should have checked that off too. It's given as minus 25. So basically, once we have the mass flow rate from this equation, we plug it in above. The only unknown is the exit velocity. So there's part of what we need. But then let's also keep in mind that there's a relationship between volumetric flow rate and the velocity. I'm sorry, I said that wrong. There's a relationship between the volumetric flow rate and the mass flow rate. We know that the mass is equal to the volume over specific volume. We know that the mass flow rate is the volumetric flow rate over the specific volume. We're trying to find the volumetric flow rate at state point 2. So we can very easily find that just using this equation. So we find V dot 2 is just the mass flow rate times the specific volume of 2. So we have to make sure that once we go into our property tables, and find the enthalpy data at the discharge point 2, we also got to find the specific volume at point 2 so that we can solve the problem. So just like most of these problems, we're using mass flow relationships, we're using the first law, we're using our data from our tables, we're making a variety of assumptions, and then we just solve the problem. So hopefully you see that the problem is now solved. That's the hard part, right? Thinking about it, setting it up, knowing how to do it. The easy part is just taking the data out of the tables and then finding the results. So let's just do that. We'll start at P1, T1. We're told that it's steam, although if you don't believe the author, or if the author just says water or H2O, well, you can do the usual check. I mean, you'll find that at this particular temperature, the pressure is less than the saturation pressure, it's superheated, or at this temperature, or at this pressure, the temperature is greater than the saturation temperature, it's superheated. Either way you do it, it's still superheated. Or you can just do it what I call a brute force method, just hunt around the tables, and eventually you'll find the right property data, right? I would much rather you kind of do that little test and just know which table to use so you don't have to waste 5 or 10 minutes just trying to find your data. All right, so we know this comes out of table A6. We know that we need specific volume data to find the mass flow rate, and we know that we're going to need enthalpy data for our first law. So V1 is 0.38429 cubic meters per kilogram, and H1 is 3267.7 kilojoules per kilogram. And we'll do the same thing at point 2. So at P2, T2, well, once again, we can do our little test. We will find that it is indeed still superheated. So we need P2 and H2. Okay. Okay again. I guess I'll just ignore that. Anyway, so the specific volume at point 2 is 1.31623. What was that? Did one of you put a beeper up here too? I did something like that to my high school math teacher once. He was not pleased. Actually, he laughed about it in the end. He was not pleased. Anyway, so we find the specific volume. We also find the enthalpy. It's 3072.1 kilojoules per kilogram. So now we have all the data we need. Let's just go through the math. We'll go back up to the mass flow rate equation. So we just plug in the data that we already have. We know that the velocity is 10 meters per second. The area is 0.08 square meters. The specific volume is 0.38429 cubic meters per kilogram. We do a little math and we get 2.082. Let's see, kilograms per second, which are the right units. So probably did that right. Next, we want to solve our first law equation. So Q dot equals M dot times the enthalpy change plus kinetic energy change. So just plug in some numbers. So first on the left-hand side, we have minus 25 kilojoules per second. On the right-hand side, we have our mass flow rate. The enthalpy change, so 3072.1 minus 3267.7 kilojoules per kilogram. And then, I forgot to do one of my equations, didn't I? We need, oh no, I didn't. I'm sorry. I couldn't find V2 and then I realized that's what we're looking for. So V2 squared minus V1 squared, so that's 10 meters per second squared, and then divided by 2. All right, so you can see that we only have a single unknown, which is the exit velocity. The units look a little squirrely, don't they? You'll see that we've got meters squared per second squared units in the kinetic energy term and kilojoules per kilogram in our, well, enthalpy change term. And it doesn't seem entirely obvious how we're going to make the appropriate change. But there's always something we can do. I mean, we know that a kilonewton meter is a kilojoule. We know that, let's see, what am I missing? A Newton is a kilogram meter per second squared. Kilogram meter per second squared per Newton. Oh, and then we also know that there's 1,000 newtons in a kilonewton. So we need a 10 to the third in the denominator. I really need to move this right-hand bracket out further and leave myself enough room. So we also have a 10 to the third in the denominator, which again is going to be newtons per kilonewton. And now you can see that everything works out properly, right? Everything cancels out except kilojoules per kilogram. So this is important. Effectively, what 1,000 does is it allows us to convert meters squared per second squared into kilojoules per kilogram. So always include that in the denominator. I will note that if you have a problem in the British system of units, you have an entirely different conversion factor, right? It's not going to be 1,000. You'll just have to go into the inside back cover of your textbook, and it actually gives you the conversion from BTUs per pound mass into feet squared per second squared. And it's not a small number, by the way. It's something like 25,037. I mean, it's a big, big number. So in the British system, by not dividing by that 25,000 number, it definitely will give you an error. I mean, this will give you an error if you're off by a factor of 1,000 as well, so you don't want to forget it here either. Anyway, solve for the exit velocity, and we get 606 meters per second. And then the very last step would be for us to find the volumetric flow rate. So we found earlier that this is just mass flow rate times the specific volume. So plug in the numbers, 2.082 kilograms per second. And again, we're finding the exit velocity, so we need the exit specific volume, so times 1.3162 meters per kilogram. And we go through this and we end up with 2.74. Let's see, meters cubed per second, which is correct. Okay. So that's just one example of a single stream steady flow process involving a pure substance like water. Any questions? Yes?
You have to convert that one because the other terms are in kilojoules. That one would technically be in joules.
You mean if we didn't divide by the 1,000?
Yeah, for that
yes,
term.
Yes. Yeah, I mean, you can do the same thing. And I mean, for instance, I could have just divided by 1,000 joules per kilojoule, and then I would have said that a Newton meter is a kilogram meter per second squared. Or sorry, a Newton is a kilogram meter per second squared. No. Yeah, that's right. If I convert from joules to kilojoules, then I would have kilonewtons, and I'd say, well, again, kilogram meter per second squared. And the units would still work out properly. And, yeah. So that's where that comes from. Any other questions? All right, so let's do another example problem. This one's out of the 7th edition of this book, 554. So in this particular problem, it's still a single stream steady flow process, but now we have an ideal gas, or we have a gas. We haven't concluded whether it's an ideal gas. So Let me just leave the bottom of this one. All right, so 554, and let me read it. In the 7th edition. So it says that we have argon gas, and it enters an adiabatic turbine steadily at 1600 kilopascals, 450 Celsius, with a velocity of 55 meters per second, and it leaves at 150 kilopascals with a velocity of 150 meters per second. It gives us the inlet area of the turbine as 60 square centimeters, and it says that the power output is 190 kilowatts. Determine the exit temperature of the argon. Okay. So this one's a turbine. We always show turbines as trapezoids. If you look at a turbine in cross section, they always get larger as the substance flows through the turbine. Its pressure is always going to drop. The specific volume is always going to rise. So in the real world, you need to have a casing that's increasing in size to accommodate that larger volume. So we always have an increasing volume for the turbine, and therefore we show these as trapezoids, increasing left to right. It's argon gas, so it's got argon inside. It says it enters an adiabatic turbine, so you need to remember that adiabatic means no heat transfer. You can think of this as a well-insulated turbine. If the author had said well-insulated, that would have been exactly the same. It's giving me the inlet pressure and temperature. So 1600 kilopascal, 450 C. And the velocity, 55 meters per second. And gives me exit pressure, P2, 150 kilopascal. And exit velocity, 150 meters per second. The inlet area is given, but not the exit area. So A1 is 60 centimeters squared. So again, we're going to have to convert this. So we divide by 10 to the 4th. We get like 0.06 square meters. And finally, gives us the power output. And this is power output, so it's a positive term. I like to put a plus sign just to remind you about that. That's 190 kilowatts. And we want to find the exit temperature of the gas. Now here, as we look at this problem, it doesn't appear to be significantly different than the previous problem. I mean, we're given the same kind of inlet and exit information. In this problem, we're given that there's no heat transfer, but there is work. In the previous problem, there was heat transfer, but no work. But besides that, it sounds pretty similar to the other problem. Let us look at some of the equations we might use. So, first of all, it's again a single stream steady flow process, right? Like all turbines are. So, first law, single stream steady flow, heat transfer minus rate of work equals a mass flow rate, enthalpy change, plus kinetic energy and potential energy changes. Although here we can again cancel out quite a few terms. I mean, we're told that it's adiabatic or well insulated, so there's certainly no heat transfer. We also know that there's probably no significant height change between the inlet and the exit from the turbine. I mean, the turbine is going to sit there on some turbine deck somewhere, and piping is probably going to be more or less at the same elevation going in and out. So you could also just neglect the kinetic energy change term. So we actually end up with a version of the first law that says minus power equals mass flow rate times enthalpy change plus kinetic energy change. So this is the version of the first law that we're going to use. Now, this problem is a little bit different than the last problem. I mean, we are given both the inlet and the exit velocities. We are given the power. We are given the inlet state, right? We have two independent properties, pressure and temperature, so we know H1. So it would appear that we don't know the mass flow rate or the enthalpy. But again, we don't want to forget our mass flow rate. We know the mass flow rate is velocity times area over specific volume, and we are given, well, velocity and area, and because we have two independent properties at the inlet, we know that we can somehow go into our table or use some means to find a specific volume. So we definitely have all of our properties at state point 1, so we can find the mass flow rate 2. The only unknown really is the enthalpy at 2. Now here's where we have issues. When we deal with a gas, the only method that we have used and that we will be exposed to in this class for solving problems that involve gases is the methods that involve an ideal gas. But we have no choice but to assume that it's an ideal gas. I'm not even going to bother to check to see whether it's an ideal gas or a real gas, because it turns out it's immaterial. If we only have the ideal gas method to utilize, then we have to use it, right? So we assume that it's an ideal gas because it's the only method we really have. And since it's an ideal gas, we know, therefore, that any enthalpy change is going to have to equal Cp times the temperature change. So we're going to have to plug that back into the first law above. In fact, that even makes the problem easier, right? If we can find the value of Cp, then we should be able to solve for my one and only unknown, which is just going to be the temperature. But here too, there's another little bit of a problem, and you're going to have to kind of get used to these problems over time. Let me go to the property tables on this one and just illustrate the problem. We know that what we'd really like to do is assume that it's an ideal gas, and we would use variable specific heats, but that's a method I said we're not really going to use because then all you have to do the whole integration of Cp dt. So the next best alternative would be to assume a constant specific heat, but at room temperature, right? So at the average temperature of the problem, but we don't know the final temperature, so we really can't find the average temperature. So what do? Well, it's not as difficult as it seems. We're kind of lucky in one regard. It turns out that for argon gas, in table A2, those are gas tables, right? Well, here's table A2 part A. It certainly gives me room temperature data, but on the table of ideal gas over a range of temperatures, it doesn't have argon. So even if I knew the average temperature, I don't have the data that's available to me even if I wanted to use it. So we have no choice, right? The only choice we have is to use table A2 part A and just assume that it's an ideal gas and that the properties we're going to use are at room temperature. So it's assumed it's ideal gas. I'll just note here that we'll take Cp at room temperature, table A2 part A, and we always call this a Cp, okay? So let's just rewrite the first law again. So the negative of the power equal the mass flow rate times, and then here we have Cp times temperature change. That's the enthalpy change term, and then plus the negative change. Other terms have already gone away. So again, we have everything we need. We start by going into our tables. We find the appropriate data for Cp. We also are going to have to use ideal gas equation to state, aren't we? Remember that we need the specific volume up here at point 1. So we know that Pv equals RT. We can apply this at state point 1 for the organic gas, or if you will, V1 is RT1 over T1. So when we get to our tables, right over here, not only are we going to have to find our data for Cp, but we're also going to have to find, the gas content. So let's just do that. So for table A2A, we have CPO, and that's equal to 0.5203 kilojoules per kilogram per Kelvin, and the gas constant R is 0.208. The same units, kilojoules per kilogram. So now let's kind of work backwards and find what we need to find. So let's find the specific volume of the inlet conditions first. Then we define the mass flow rate, then we just solve the first law, and we're done. Right, so plug in the numbers. 2081 kilojoules per kilogram per Kelvin. The temperature at 1 is 450, so we need to add 273.15 to turn Celsius into Kelvin. If you don't use Kelvin, your answer is wrong. We have to divide this by the appropriate pressure, so 1600 kilopascals. Yeah, we know a kilonewton per square meter is the same thing as a kilopascal. And we know that a kilojoule is a kilonewton meter. So this will basically take care of all the units, basically a bunch of identities, and we finish our math. Units come out right. We get 0.09404. The only units that are left are meters cubed and kilograms, which is what we want, right? Anything else makes sense? All right, so now we have our specific volume. Now we can find the mass flow rate. So the mass flow rate is the velocity area over specific volume at 1. So the velocity is given, it's 55 meters per second. The area is given, 6 square meters. Specific volume is found. And you can see that the length units all cancel. We just get kilograms per second. 3.509 kilograms per second. So mass flow rate is done. And last but not least, let's finish. So we have the negative of power. Again, I want to remind you, don't confuse the sign within the equation with the sign of the work term. Same thing applies to the heat transfer term, right? Work is being produced by the system. It's worked out. It is a positive number, but there's that minus sign as part of the first law. So don't get rid of the minus sign because you know there's a positive work term. Leave the equation be. I mean, it's the first law. You don't want to mess with that. You just want to make sure the signs are right in all the other terms. So negative of a positive number, and then just throw in all the rest of what we have. So 3.509 kilograms per second, CP 0.5203 kilojoules per kilogram per Kelvin. We now have a temperature difference. Let me again remind you that a temperature difference in Kelvin is the same as a temperature difference in Celsius. So I'm just going to leave these in Celsius. T2 is my unknown. T1 is 450. And this is degrees Celsius, but again, we're talking about a difference in temperature, not talking about an actual temperature. So a temperature difference in Celsius and in Kelvin would be the same, right? 1 unit of Celsius is 1 unit of Kelvin. Anyway, then we add to that the kinetic energy change. So we have 150 squared minus 55 squared over 2. The units are going to be meters squared per second squared. And again, we need to divide the whole thing by 1,000 in order to convert our meters squared per second squared into kilojoules per kilogram. So go through the mathematics. You only have a single unknown. You solve, and we end up with T2 of 327 degrees Celsius. Now, if you want to do it in Kelvin, that's fine. You'll end up with about 600 degrees Kelvin. Just add 273 to that. So it doesn't matter. Either way is fine. I just like to save time if I can, and I know that the temperature difference in Celsius is the same as Kelvin, so no need to really convert it into Kelvin unless we want to. There you have it. Any questions on this particular problem? Now, this one is certainly different than the previous one, but only because we're talking about an ideal gas. Once we recognize that it's an ideal gas, in many ways, it's easier than the previous problem, and we just solve the first law directly for the unknown temperature. And if this were a regular problem, if it was an ideal, if it were a pure substance problem like water or the refrigerant 134A, we would have an unknown enthalpy, and then we would have to go into our property tables at the given enthalpy and pressure and by interpolation, try to figure out what the temperature is. That's not an easy process, especially the whole business with interpolation. So, this saves you an interpolation. It's a little bit easier of a problem. Of course, I guess it's also harder in the context that you have to use a specific volume from the ideal gas equation of state. You can't just look it up in the property table. So, different problem. Not really any harder, not any easier, just different. And again, make sure that because it says enthalpy change, you're using Cp times the temperature change within the first law equation. So any more questions? Okay. How about another one? Let's do a hard one. Actually, you'll find that it's not that hard either. Okay, so this one is from the current version of your book. It's problem 580. So the problems that we've looked at up until now have been single stream steady flow problems. Why not look at a multiple stream steady flow problem like a heat exchanger? So that's what this particular problem is. So 580 is a heat exchanger problem. You can think of this as exactly what's going on underneath one of those panels up there in the ceiling. Okay? There is a source of hot water or steam that's going through some little tubes, and air is being blown across it. The water is losing heat, exchanging with the air, and the air is getting warmer. Let's say you were in the business of trying to design the ductwork for that heat exchange system that's buried up there in the ceiling. You need to know how much volume needs to flow through per unit of time in order to determine what is the proper volume for the ductwork. So, you shouldn't think of this as just an academic problem that requires you to find a certain volumetric flow rate. This is a real problem. Some of you may actually get into the HVAC business and do this kind of stuff for a living. Somebody's got to figure out what kind of ductwork and piping and all that one needs in a home, in a building, a commercial enterprise. So let's read this problem. It says in a steam heating system, air is heated by being passed over some tubes through which steam flows steadily. Steam enters at 30 psia, 400 Fahrenheit, at a rate of 15 pounds per minute, and leaves at 25 psia, 212 degrees Fahrenheit. And then it says air enters at 14.7 psia, 80 degrees Fahrenheit, and leaves at 130 degrees Fahrenheit. So we want to find the volumetric flow rate of the air at the inlet. So, the drawing. They don't show any drawing there. By the way, if I haven't mentioned this before, some of the problems that you're going to see have that little disk icon and a little EES on there. That stands for Engineering Equation Solver. Once upon a time, when you guys actually bought hard copies of the book, there would be a disk that came with the book, and it had various problem-solving tools on there. The author would like you to use that for this problem, but I don't see any point in that. It's not like you're going to be able to use computers on exams in this class, and it's not really that difficult of a problem, so I don't know why one needs computerized methods anyway. But still, just ignore that. Some of the problems I will assign, some of the other problems I will assign, perhaps I should say, you will have the little EES disk logo. Just ignore it. I do not want you to use that. I want you to just solve it by hand. All right, so the diagram. So here is my heat exchanger. And let's say that we have air moving in one direction. So this is my airflow, and the air is going to come in at 1 and go out at 2. And then we're going to have the steam, which is just H2O, moving through these tubes, which crisscross through this heat exchanger. Think of it as like a coil that contains water, or some pipes that contain water. So we'll just let 3 be the inlet and 4 be the exit. Right, so you always want to start with the diagram like that. Now it says it's being, well, first of all, it says it's flowing steadily, so that means it's a steady flow process. Steam enters at a certain pressure and temperature, so the steam is 0.3. So P3 and T3 are given. 30 psia, 400 degrees Fahrenheit. and it says that the flow rate is 15 pounds per minute. So I'll just put m dot s for steam. And this steam flow rate, again, is 15 pounds mass per minute. Those are never appropriate units. You always want to turn it into seconds. So let's just divide it by 60, so we have 0.25 pounds mass per second. So that's the steam flow rate. And that would be the same at the inlet and as the exit, right? I mean, it's a steady flow problem. So this equals m dot in at 3 equals m dot out at 4. So just be aware of that. And then it gives me information about the exit conditions. So it says 25 psia, 212 degrees Fahrenheit. So T4 given. Then it gives you some air information. So it says the air enters at 14.7 psia and 80. So the air is 1. So P1 equals 14.7. P1 is 80 degrees Fahrenheit. And it leaves at 130 degrees Fahrenheit. So P2 130. So this is how I like to set up these particular problems. It also says determine the volumetric flow rate of the air at the inlet. So in other words, we're trying to find that one. So it's certainly not going to be obvious how to solve this problem. You might expect, though, that it's a first law problem because, well, they're all first law problems. So somehow we're going to have to incorporate the first law into this problem. But how? How are we going to incorporate the first law? Well, let's just note that to find the volumetric flow rate, that's the mass flow rate times specific volume. So if we're trying to find this for the air at 1, we need the mass flow of the air, and we need the specific volume of the air. So, well, that doesn't really give us any clues as to why we might need to solve the first law. Well, or does it? How am I going to find the air mass flow rate? Again, this is at point 1. I can't find the mass flow rate unless I use either one of the mass flow rate equations, a continuity equation, or I use the first law. Well, the mass flow rate is velocity area over specific volume. That doesn't help me out. I mean, I can plug it into here and then the specific volume cancels and it doesn't help me in any way. But what about the first law? Well, it's steady flow, but not single stream. In other words, the equation we're going to use is heat transfer minus work equals the sum overall exit flow paths of m dot E HE minus the sum overall inlet flow rates of m dot I to HI. Now, why didn't I put kinetic and potential energy change terms here? I really don't need them. I mean, I could need them, but they don't give me any information. They don't tell me anything about the physical size of the piping or the duct work. Yeah, they give me a mass flow rate, but unless I know some area information, I can't find the velocity even if I wanted to. So, the author perhaps could have said something to make it clear that you should neglect the kinetic energy. I don't necessarily want to neglect the kinetic energy, but I don't have enough information to find it no matter what I want to do. But besides that, I might note that we're still always going to keep the velocities low. We don't want to erode the inside of our pipes or our ducts, so chances are that the velocity is low anyway. So given that we don't have enough information to find any velocities, and given that the velocities are typically going to be small numbers anyway, I can just neglect any changes in kinetic energy. And the same thing with potential energy. I mean, there may be a height change associated with this problem, but they certainly haven't given me any information about the physical size of any of this equipment, so I don't know how to find the height change. Again, even if I wanted to, I just don't have enough information, so I have no choice. I just have to neglect the change in potential energy. So we know that within the first law, there are kinetic and potential energy terms here, but I've simply neglected them, not so much out of choice, but just because I have to. I just don't have the information in order to find that. Now, again, if I had been given something like the area of the pipes or the ducts, then that's different, right? Then I can find relationships between area, velocity, specific volume, but I can't because I don't have that information. Right? So having said all that, this is a version of the first law. Now, another thing that they didn't really tell me was what's happening with regards to heat transfer or work. I would have much preferred if the author said that this is a well-insulated heat exchanger. I mean, frankly, they're always well-insulated heat exchangers. You know, you're paying a lot of money for the heat that's being used to heat up this building or transferring heat within the heat exchanger, same thing, right? Why wouldn't you insulate it if you're trying to minimize your costs? So I would then assume that there's no heat transfer, so Q dot 0. And with regards to work, well, for these types of devices, it's always 0. I mean, it's a passive device, right? There's no moving parts, there's no work of any kind, so certainly it would make sense to calculate, to estimate that the work is equal to 0 as well. All right, so this term goes to 0, this term goes to 0, and we're really just left with the right-hand side of this particular equation. So let's work on that. So first law, keep working on the first law. So we have two exit flows, right? We have the air that comes out and the water that comes out. So we have m dot 2H2 plus m dot 4H4. And then we have two inlet flows, right? The air and the water come in at 1 and 3. So we have m dot 1H1 plus m dot 3H3. Now let's just combine the terms that deal with water and then further combine the terms that deal with air. So we have m dot 1 and m dot 2 times H2. But remember, it's a steady flow process. We should note that m dot 1 and m dot 2 are both the same. That's just the airflow. So maybe I shouldn't even bother using a 2 anymore. Let's just change that to air. M dot 1 is air, m dot 2 is air. So we can just write this as m dot air times H2 minus H1. And then we add to it, well, let's combine the steam terms. So we know 3 and 4 are both steam or water terms. I could write m dot 3H3 and m dot 4H4, but let's not. Let's just note, like it says up above, that m dot 3 and m dot 4 are the same, and those are both equal to m dot steam. So let's write this then as m dot steam, and then multiplied by H4 minus H3. So remember what we're trying to solve for here, right? We're trying to find the volumetric flow rate. We know that we can find the volumetric flow rate once we have the mass flow rate in a specific volume. And perhaps you can see now that we can actually find the air mass flow rate by solving this equation. Note that we know the thermodynamic state at 3 and 4, right? We're given both pressures and temperatures. So H3 and H4 are known. We're also given the steam mass flow rate, so that term is known. Let's put these little checks here. We also know the air conditions. We know two properties of the inlet, so we should be able to find H1. And for that matter, we can certainly make an assumption as to the pressure associated with the air at the exit. Quite frankly, I mean, it's air in a big duct. Okay, yeah, there's some little tubes crossing through it, but there's not going to be any measurable pressure loss. The pressure at the inlet to that duct is really going to be the same as the pressure at the exit from that duct. It's all just atmospheric pressure. So it turns out we really do know the pressure at point 2, even though they haven't explicitly told us. It certainly makes sense that we can assume that P2 and P1 are the same. So let's just note down here another assumption. Assume that P2 is equal to P1 with 14.7 PSI. Okay. Nonetheless, what this does allow us to do is conclude that we can find the enthalpy at point 2, and the only unknown in this equation is the air mass flow rate. So the air mass flow rate is going to be found from the first law. We will simply plug it into the equation above and find the volumetric flow rate, except we do need the specific volume, but that's okay. It's a specific volume of air we need, and air is a gas, and we're going to have to assume that it's an ideal gas, not just to solve for the ideal gas equation of state, but also for the enthalpy change term, right? We don't have the ability to use air tables. Now, I will make a note here. Table A17 in your textbook are air tables, but we're not going to actually use those air tables not until we get into ME302. We're just always going to assume that air, like any other gas, is treated as an ideal gas. We'll use the ideal gas equation of state. We'll use specific heats at constant pressure, constant volume, whichever is appropriate. But don't use table A17. I did notice, by the way, that there were a couple of students that did use air data at table A17 for the one homework problem that dealt with air. And it wasn't like it was incorrect. I mean, there is enthalpy data on there, but it's, again, not something we're going to do in this class. Wait till ME302. All right, so let's just continue. We know that we need the specific volume, and we have to assume that it's an ideal gas, because quite frankly, the only method we have to solve first law problems is ideal gas. And therefore, let's rewrite the first law. So we have the following. We have 0 equals m dot air, H2 minus H1, well, this is going to be Cp times T2 minus T1, and then plus m dot steam, H4 minus H3. All right, so this is what we're going to have to do now. Well, continuing, we talked about finding the specific volume of 1. Well, we know that PV equals RT, so we're going to have to use this equation in order to find the specific volume at 1. And then the next thing that we have to address, and really the last thing we have to address, is, well, what about CP? Remember that it would be best if we were able to find CP at the average temperature of the process, and indeed we can, right? Turns out that we're given both the temperature of the air at the inlet and at the exit. So, you know, we can very easily find T air average. That's just going to be T1 plus T2 over 2. And then we'll be able to find CP at that average temperature, and we'll do this all here in a minute. So let's just go back up to the first law. Since we do have the temperatures at point 1 and point 2, then we can find the average temperature, and we can find Cp at the average temperature, which would be the most accurate way for us to find this, which is the enthalpy change, right? All right, so any questions at this point? I mean, there's a lot of things we've had to assume. This is not an easy problem, but mathematically it's not difficult. I mean, it's all just junior high school level algebra, right? So, I mean, there should be no math issues. They're conceptual issues, they're data issues, they're equation issues, but they're not solution or math issues, right? So, think about this problem. One other thing I might want to note, since we've used ideal gas assumption and we're not using enthalpy change, we're using Cp times temperature change, it turns out that all that I described before about assuming the pressure is constant, it doesn't even matter, right? We know that for ideal gases, the properties of enthalpy and internal energy are strong functions of temperature, but very weak functions of pressure. I mean, that's why we're able to use specific heats to begin with. It doesn't matter what this pressure is. We don't even need it, right? Cp is only a function of temperature. They could have given me any pressure at the exit, and I would have solved this problem exactly the same way. Now, that doesn't mean what I described earlier is invalid. I mean, sure, you're talking about a heat exchanger, which is largely just open space. How can you really have a big pressure difference between one end and the other end? I mean, you know, take a big box. Is the pressure on the left side of the box different than the pressure inside at the right side of the box? No, it's just one big volume, right? And that's kind of how heat exchangers work. They're just one big volume where you've got some tubes passing through. There may be a slight pressure drop, but not that significant. Certainly we're going to be able to ignore it. All right, so now let's continue. All right, so let's find the average air temperature, first of all. The average air temperature is, what, 130 plus 80 divided by 2. So that's what, 105, and that's in degrees Fahrenheit. We go to table A2, part B, and I guess I can get rid of this now. We've all seen the problem statement. It's actually A2E part B, isn't it? Okay, so A2 and A2E are the same, just different units. Here it gives me air data at room temperature. Here it gives me air data over a wide range of temperatures. Now note that these are temperatures in Fahrenheit. You can see that at 100 degrees it's 0.240, at 200 degrees it's 0.241. I theoretically have to interpolate between 100 and 102, but I mean we're going to get what, 0.24005. Let's just ignore that, and at 105 we'll just say that it's 0.240, and that'll be in BTUs per pound mass per degree. All right. So this is what we're going to get at the average temperature of the problem. We may as well look up the value of R while we're here. Now it doesn't give me R in table A2, at least not A2 part B, but it does give me R in A2 part A. Now, do I want to use this? Honestly, there's better data. Remember that A1 also has gas data, and you may recall a statement I made a few weeks ago that there's two different values of the gas constant in table A1, and since we're only going to use R within our specific volume equation, that is our ideal gas equation of state, then we're going to have to use pressure in the given units of PSIA. I might as well use the value of R that also has units of PSIA. So that's just this, right? So it's 0.3704. So it turns out we actually want to use A1. And again, I actually really put an E in here to use these units. But we get 0.3704 PSIA foot cubed per pound mass. Okay, so moving on, let's find a specific volume at point 1, as long as we're still here. So V1, there's our T1 over P1, so 0.3704 PSIA foot cubed per pound mass per R. We definitely have to use the temperature in Rankine. Keep in mind that this says T1, not T average, so we're finding specific volume in 1, we better use the temperature at 1. So 80 plus 459.67 converts from Fahrenheit to Rankine. The pressure at 1 is 14.7 PSIA. You can see that the units work out great. And we get the specific volume with the appropriate units, 13.61 cubic feet per pound mass. We're going to actually save that for later. What we need is to find the air mass flow rate from the first law. Then we finish the problem up and find the volume. So let's see about doing that. So back to the first law. Well, since the first law is still here on the same page, maybe I just won't bother to rewrite it. I'll just show what it'll be there or again. So let's just write what we know, what we don't know. We're trying to find the air mass flow rate. That's my unknown. Cp at the average temperature we found, 240 BTUs per pound mass per water. We now have T2 minus T1. So T2 is 130. T1 is 80. By the way, up here I kind of reverse the two. I mean, it doesn't change the mathematics. I just go to the wrong order. Again, I want to note that we're talking about a temperature difference in Fahrenheit, but it's the same as a temperature difference in Rankine, just like in the last problem. So yeah, you can go ahead and add 459.67 to each of those two numbers, and you still end up with exactly the same. So we end up with essentially 50 degrees Rankine as a temperature difference. The steam mass flow rate has been given to us, so 0.25 pounds mass per second. And we have to look up some enthalpy data, which I did not quite do yet. So this data is going to have to come from our tables. We know that at least at state point 3 it's steamed, but what about state point 4? Well, let's figure that out. So at P3 and at T3, it turns out that it's superheated steam. We'll just go into A6E, and we can find the enthalpy at point 3, and this is 1237.9 BTUs per pound mass. Now again, take the test if you need to. Certainly it could be shown that the given temperature is greater than the saturation temperature at 30 psia, which is your given pressure, so it's clearly superheated. But again, what about 0.4? Right across the lines. Well, let's see. I'm not going to assume that it's superheated, and in fact, it isn't, is it? I mean, you should be able to see that just by looking at the given data. The given temperature is 212 degrees Fahrenheit, and we know that that's the boiling point of water at standard atmospheric pressure of 14.7 psi. Without even looking at the tables, I know that my given pressure of 25 is greater than 14.7 psi, that is the saturation pressure at 212 degrees Fahrenheit, so it has to be a compressed liquid. So since P is greater than Psat at the temperature of 212 degrees Fahrenheit, it's compressed liquid. Now, it would be nice if we had good compressed liquid tables, but we don't. We know that we don't. So we just make the usual assumption. We say that for a compressed liquid, it has the same properties as a saturated liquid at the same temperature. So H4 is actually HF at 212 degrees Fahrenheit. And that number, if we just go into the tables, is 180.21 BTUs per pound mass. So we plug the numbers in. 180.21, 1237.9 BTUs per pound mass. Well, if you go through the entire problem, then you should be able to see that everything's going to cancel out. The units are going to work out properly. Let's put that here. And we can solve for the air mass flow rate at this point. And we end up with 22.04 pounds mass per second. And then lastly, we go back to our equation that says volumetric flow rate of 1 is the mass flow rate times the specific volume of 1. So we have these numbers now, right? They're both shown above. So we have 22.04 pounds per second times 13.61. Keep in mind that m dot 1 is m dot air, right? They're the same. And this is going to be cubic feet per gallon mass. And we end up then with the final answer of 300. So this equals 300 cubic feet per second. Wow. I tell you, if you could solve this one, you should be able to solve anything, right? This has a pure substance in it, water. It also has natural gas in it. It requires you to use property tables for the water. It also requires you to use the ideal gas assumption and specific heat times the temperature change to get enthalpy change. About the only thing I can really do to make this more complicated is give you velocity data so that you have to include kinetic energy terms, and maybe tell you that it's not well insulated so that you have a certain rate of heat transfer. That's going to be an even more complicated problem, but you'd use the same methodology. So this is a good problem. It's long, it's complicated. but it's not undoable. It's just hard. It's, welcome to engineering, right? Okay, so I'm done for the day. Are there any questions on any of these problems? Yes?
So is it common for, if the steam is being used to heat this air that's passing through the toilet, is it usual for that phase change to happen?
Yes, right? I mean, you can generate a much greater energy change at a particular temperature or a particular temperature and pressure by allowing the substance to condense. So, pressure and temperature remain constant, or at least more or less constant, while the energy that's transferred is really quite significant.
Because of that whole phase change.
Yeah, because of phase change.